the first line here.
1.58 times 10 to the negative 7. Dash. 0. And 0.03830015. Minus that. Plus that. Plus that.
All right, so I think I could fill in the rest here. On tests and stuff, you should write the KB3 expression in case there's some math error. You would get more partial credit. And so how did you solve for x?
Simplifying assumption.
Okay, so you use the simplifying assumption. If we use the simplifying assumption, what did x come out to?
5.85
Times 10 to the negative 18. 5.85 times 10 to the negative 18. So here we have 10 to the negative 7. So 10 to the negative 18 change over 10 to the negative 7 was 10 to the minus 11. Times 10 squared gives us a 10 to the minus 9. You know, just roughly, ballpark. 10 to the minus 9% change. Right? And so that's justified. That's good. And so let's go ahead and plug in the numbers here. So I'm going to write this in decimal form. So that's 6 zeros, 1, 2, 3, 4, 5, 6, 1, 5, 8. Minus, what we're going to have here is 17 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 5, 8, 5, 3, 6, 8. So what does this give us? It gives us 0.6 zeros, 1, 2, 3, 4, 5, 6, a 1, 5, 7, 9, 9, 9, 9, 9, 9, 9, 9, 4, 1, 5. So did we lose much? No, this was what we call negligible change. So this is not going to perturb step 2. We did gain a significant amount of phosphoric acid. So this is 5.85 times 10 to the minus 18 molar here. And then we did gain a little bit here, 0.038300158. And then we need 17 digits, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 5, 8, 5. So we added this much, this 585 on top of this. Was that a significant addition? No, it's insignificant. And so we barely added any hydroxide. And we did add a significant amount of phosphoric acid. And we really didn't lose much dihydrogen phosphate. All right, this is step 3. And the only other hydroxide producer would be KW. All right, so let's go ahead with KW here. We'll call it step 4. That would be H2O liquid plus H2O liquid. This gives us hydronium and hydroxide. And so I'll work on this with you. So we're going to carry down the hydroxide. The hydroxide's not done yet. We're going to get a little bit more from KW. So we have 0.0383 molar. How much hydronium do we have initially? Why 0? Shouldn't we have 1.0 times 10 minus 7 molar? Shouldn't we? So isn't it 1.0 times 10 minus 7 molar? Well, two ways to answer. Yes. You know, but that's too much hassle. This is called the Le Chatelier's method of solving it. We'd much rather reset it down to 0 and then start from there. Because what we'd have to do is we'd call this 1 times 10 to the minus 7, then we'd have to add 1 times 10 to the minus 7 molar to this, and then do a shift left. Pain. Calculations of pain. Much easier, just go 0 and 0. And this came from step 3, just add it in there. And so the change is going to be plus X molar, plus X molar. I don't know what Petrucci calls that. Did Petrucci call that a reset? Probably not. But does Petrucci do that for every single problem? Yes, he does. He doesn't want to solve it the other way because it's too much of a pain. And so, some people say, but this reset stuff's not in the book. It is in the book. It's just not expressed in the same manner. Okay, and so over here we're going to have 0.03830 plus X molar. And so KW is equal to 1.0 times 10 minus 14, which is equal to the hydronium times the hydroxide, which is equal to X times 0.03830 ... plus X. Here we'll just use the simplifying assumption. So this is going to be X times 0.0383 ... And so therefore X is equal to 2.61 times 10 to the negative 13. That's what I get. 2.61 times 10 to the negative 13. So our change is this, 10 to the negative 13. Our initial is this, 10 to the minus 2. So 10 to the minus 13 divided by 10 to the minus 2 is 10 to the minus 11. This again would be about a 10 to the minus 9% change, which is extremely small. Therefore, the simplifying assumption should work very well for this. So we'll go over here, 2.61 times 10 to the minus 13. Did we already double check the K here? Did we double check that K? Yeah, you know what? Before I finish this calculation here, if there's a mistake here, then I'll have to repeat step 4. So let me stop step 4 and just make sure there's no mistake here. So this was 5.85 times 10 to the negative 18 divided by actually, times 0.038300158. Did someone do it? Does it check out? Yeah. Okay. All right, so over here, this is going to equal 0.03830 dot 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 plus 2.61 times 10 minus 13. A lot of zeros. And so this is going to come out to about 0.03830 dot dot dot. And so what we did was we started off, where was most of the hydroxide produced? You know, step 1, 2, 3, or 4. Take a look at the hydroxide. Let's follow the hydroxide down the line. In step 1, did step 2 add much? No, nor did step 3, 4. And so if we were just interested in the pH, I would have stopped at step 1. Sometimes if you're interested in the pH, you have to stop at step 2. When do you know it's okay to stop at step 1 versus step 2? Yeah, when there's not that big of a K value. Like for example, if step 2 had a K value of 10 to the minus 7, would you bother doing step 2? I wouldn't. If step 2 had a K value of 0.011, would you bother doing step 2 for pH calculation? I would, because that's significant. It's a pretty big K value, so I would worry about it. But for most of these problems, you know, and so step 1's adequate. But why did we do all these steps? We did all these steps so that we could get the inventory. And so the final concentration of hydroxide is this, the final concentration of hydronium is this. This hydroxide gets carried down, the dihydrogen phosphate is this, and the monohydrogen phosphate is this. And so what we'll do is we'll oh shoot. Oh no. I got mixed up here. This is not dihydrogen, this is phosphoric acid. I was looking way up here. This is the dihydrogen phosphate. But the dihydrogen phosphate got carried down, so this is not the final concentration. This would be the final concentration here. Monohydrogen phosphate's this. This would be the final concentration here. All right, so let's figure this out then. For a beaker, if we had a beaker that was labeled 0.100 molar sodium phosphate, what would we find in the solution? We'd find sodium ions at 0.300 molar. We'd find phosphate ions at, what's the molarity of the phosphate ions? It's like 0.6, was it 0.6 something? 0.06? 17 molar. We would find hydroxide at 0.0383, over there. We would find monohydrogen phosphate. Monohydrogen phosphate's here at 0.038299. We would find dihydrogen phosphate, which ends here, at 1.5799 times 10 to the minus 7 molar. We would find phosphoric acid, H3PO4, at 5.85 times 10 to the minus 18 molar. And are we missing anything? Yeah. We'd find H3O plus at times 10 to the negative 13 mole. All right, this is what we call the solution inventory. The solution inventory just shows the species and what concentrations are present. And then to figure out the pH, we have two ways to determine the pH here. We can go from the hydroxide. If we go from the hydroxide, we would go to the POH, and from the POH, we'd calculate the pH. So to get the POH, we would just, the POH is just equal to the negative log of the hydroxide ion concentration. So let's figure out what the negative log of the hydroxide ion concentration is here. .416. And then the pH is just equal to 14.00 minus the POH. And that gives us 12.583. And so pH at 12.583, which is pretty basic, right? I mean, it's really basic. This is. The other way we could have gotten the pH is just go straight from the hydronium ion concentration. If we just took the negative log of the hydronium ion concentration, you get the same answer, 12.58. Because the hydronium and hydroxide ion concentrations are tied together. So if one goes up, the other must come down, and vice versa.
The only thing is you have to do all 4 steps in order to do.
Right. Whereas if we stopped at step 1, then we'd just go off the POH pH calc. All right, any questions about that? No. All right, the last part of chapter 16 deals with ions. The last part we're going to cover. The very last part of chapter 16 deals with, I'll talk longer than this, deals with structure and acidity. And that was supposed to be covered in Chem 1A. So we're going to skip that for now. We'll come back and look at some selected topics. But ions as acids and bases, you know, so we have things like phosphate, but we also have things like chloride, you know, bromide, iodide, nitrate, bisulfate, chlorate, perchlorate. What do all these ions have in common? You know what all these ions have in common? All these ions are the conjugate base of a strong acid. The conjugate relationship goes like this. If one species is strong, its conjugate is going to be weak. And so the conjugate base of these strong acids are very weak. Very weak bases. In fact, they're too weak to hydrolyze water. And so, for example, chloride. Chloride plus water. If chloride acts as a base, then we should form HCl and hydroxide. This would be the Kb reaction for chloride. Is it okay to erase this? And so if I'm looking at the Kb for chloride, the Kb for chloride is equal to the Kw over the Ka for what acid? Hydrochloric acid. What is the Ka for hydrochloric acid? Yeah, so we have Kw over very large, which means the Kb value is going to be very small. And so we don't even have a number for this. We just know it's very small. In fact, it's so small, we're just going to say that this Kb reaction is pretty much negligible. Therefore, if you add something like chloride in water, it doesn't change the pH. The pH just stays the same. It's neutral. Call it neutral. All these ions are neutral. But others aren't, you know. So if you had something like carbonate, carbonate is basic. In fact, that's a dibasic base because it's capable of accepting 2 protons. Carbonate, etc. are bases. And so the others you can just find on the chart. On chart. These are the anions here. Carbonate, phosphate, etc. What about the cations? For cations, we have ammonium and the amine derivatives, which would be like trimethylammonium, whatever. You know, they're all going to look the same, except rather than a hydrogen, to have some kind of hydrocarbon attached to it. And so these are weakly acidic. It's got to be H, sorry. And then we have, what else? We have other cations, like sodium, potassium. In other words, the other group 1s, calcium, strontium, and barium. These cations we call neutral. They don't hydrolyze water. But aluminum, 3+, iron 3+, etc. These are acidic and do hydrolyze water. Now, when we're thinking about ions as this is for ions as Bronsted acids and bases. There's no problem with these anions because all these anions can accept a proton. But when I think about these are not proton donors. And so why would I even be considering these as acids? And the reason is we wouldn't be considering these, group 1 and calcium, strontium, barium. These are the cations of the soluble hydroxides, which are strong bases. But these ones can act as Bronsted acids in water. And the reason is because it forms a complex. And so the first one is aluminum. Aluminum forms the hexa aqua complex, like this. When we look at that, that's aluminum 3+ with a water bonded to it. So one of the lone pairs is now used as a coordinate covalent bond. Because aluminum has a high positive charge, what happens is we get the inductive effect. Do you recall the inductive effect? Inductive effect is this polarization of the electron cloud towards this positive charge. And that's going to generate a large delta plus on that hydrogen. Versus water. You know, water isn't nearly as acidic. This stuff is as acidic as like acetic acid. This water isn't. And that's because there's no inductive effect here. There's nothing pulling the electron density out of water like this aluminum is. And so we generate a much smaller delta plus. And therefore, if you're a base, let's say you're hydroxide, then which of these protons would you attack? Now, if you're hydroxide, you would attack this proton. This one will have a much stronger electrical attraction here than this proton here. And so that makes this aqua ligand quite acidic, hence giving it acidity. So what we'll see is we'll see Ka values for this, the Ka value. In fact, these are polyprotic because there are multiple waters on there. These are typically thought as triprotic acids. All right, we'll do a calculation with that in one of the labs. But other than that, we don't do too many with the metal cations. So here, these ones are neutral. Other metal cations are acidic. definitely can change the pH of water.
This is kind of backtracking, but on the top where it says cations,
Yeah.
plus next to it, is that H and R too?
Well, it's actually HNR3, sorry. HNR3. I made a mistake. Should be HNR3. An example of this would be something like this. HC, or H, let's do HNCH3, 3. HNCH3 is going to have a positive charge on the nitrogen. And this is going to be called trimethylammonium ion. It would behave like ammonium. It would have comparable acidity. All right, any questions on this? Okay, one more thing to finish here, and that's the last cation in the analysis. These ions, most of the ions, you just look it up on the table. Let's see. What is the Kb value of the Ka value? And go from there. You aren't going to find any Ka values for these guys here. You will see Ka values for these, aluminum and iron. So going back to today's lab, magnesium 2+ is the final test. And so if we have our unknown and we add HCl to it, well, there's no reaction with magnesium. So magnesium 2+ plus chloride, there's no driving force for metathesis reaction there. So if we take solution 1 and then add our ammonium buffer to this, again, we get no reaction. But in this case, we would have expected reaction. So it's magnesium 2+ plus 2 ammonias. We would have expected reaction because magnesium 2+ with 2 ammonias and 2 waters should give us magnesium hydroxide, which is a precipitate. And that precipitate is going to be the driving force for this reaction. And so we expect this, but we're going to prevent precipitation by increasing the ammonium concentration. If we increase the ammonium concentration, that's going to shift this back to the left, preventing precipitation. And so we have to make sure the ammonium concentration is high enough to prevent precipitation of magnesium hydroxide, which is insoluble. All right, then if we take solution 2 and just add sodium hydroxide to this, then we can't stop the precipitation. This is going to precipitate. It's going to give us a white PPT. And that is magnesium 2+ plus 2 hydroxides now will form MgOH2 solid. All right, what do we do with this precipitate? Well, the precipitate from 3, we just add ammonia to that, and nothing should happen to the precipitate. That is, magnesium hydroxide won't form complexes with ammonium. So we end up with NR here. Then we take the precipitate from step 4, and then we add HCl to this, then the precipitate dissolves. So magnesium hydroxide solid plus 2 H pluses will yield magnesium 2+ plus 2 waters. So here we would either call this a metathesis or an acid-base reaction. There's a driving force for this. We're going from a stronger to weaker acid. And then 6, we're going to reprecipitate this. So we'll do solution 5. And what are we adding to precipitate it again? Are we adding sodium hydroxide or ammonia? Hydroxide? and the magnesium reagent. The magnesium reagent, what is that? Well, that turns out it's just a dye. This dye is going to give us the blue lake. And so all we're doing is we're taking the magnesium ions and then precipitating out the hydroxide while incorporating the Mg reagent. The Mg reagent is going to contaminate our solid precipitate and give it a color. It's just a dye that colors our precipitate blue. And so what you're looking for is a blue lake precipitate. A blue lake precipitate is going to be like a gelatinous precipitate. And so in order to see it, you have to centrifuge. When you centrifuge the test tube, it will pack the precipitate down at the bottom of the test tube, which is just a gelatinous, again, precipitate. And so it looks like a lake. You just formed a miniature lake on the bottom of the test tube. And above that, you should have a liquid layer, the solution, which would be like the sky above the lake. You aren't looking for a blue solution. You're looking for a blue precipitate. So be careful, because if you're just getting a blue solution, that could be a false positive, not a true positive. All right, any questions on the magnesium test? No? I'm going to stop talking.